Welcome again to the course on audio signal processing for music applications. Last week we talked about the short time Fourier transform. That offered a sound representation from which we can synthesize sounds without losing any information. And at the same time, it's a good tool for understanding, describing, and transforming sound. This week we go a step further in the direction of obtaining a higher level representation that in exchange of losing a bit in terms of the identity properties of the STFT, we gain quite a lot of flexibility and level of abstraction in the representation. This is what we call the sinusoidal model. And we will cover this topic in three theory lectures. So this is the first one. We will first present the model, the sinusoidal model, and then talked about how these sinusoids can be expressed in the spectrum and how can they be identified in what we call spectral peaks. So the model is quite simple. It's just a sum of time-varying sinusoids. So this equation, we have seen it before, but here we are emphasizing two aspects. One is the idea of summing a finite number of sinusoids, capital R. So we have capital R sinusoids, and each of these sinusoids is time varying. It has an instantaneous and a frequency value that changes in time. So changes as a function of the time index n. But we're interested in modeling the sinusoids in the frequency domain, in the spectrum. So let's see how that looks like. Again, we have seen these equations before. So if we start from a signal x, that is a real sine wave, and then we take the DFT of the windowed version of this sine wave, we see that, of course, the sine wave can be expressed as the sum of two complex sine waves that are then multiplied by the window we use. And being the sum of two exponential sine waves, we can split that into two summatories, so as separate DFTs. So we'll have the DFT of the negative frequency and a DFT of the positive frequency, each one again multiplied by a window. And these complex exponentials can be grouped together. And basically, this is the DFT of a shifted version of the transform of the window. Okay, so basically, at the end, we see that the first summatory is the DFT of the function W. So it's a big W, and the frequency index is shifted. So we have shifted the window, and is scaled by the amplitude of the cosine, by half of the amplitude of the cosine. And the other element is the same window, but shifted by the positive frequency, and also scaled by the same amplitude. So if we start from a sine wave and we want to show it the plot of one single spectrum of this windowed sinusoid, we can see it like this. So this is the positive spectrum. So we don't see the two windows, we only see the positive one. So we are seeing the positive frequencies, and so the contribution of the positive exponential. And we see the shape of the window that we use, but of course centered at the frequency of the sinusoid, which is 440 hertz, which of course we can listen to the sine wave. And this is its spectrum. So a peak centered at 440 hertz, and the phase that during the main lobe is flat, that corresponds to the phase of that sine wave at location 0. Let's make it a little bit more difficult. What happens when our sound is made up of two sine waves? So these are two sine waves, one at 440 hertz, the other at 490 hertz together, and we can also listen to that. Okay, so clearly it sounds like a modulated a signal, and in the time domain we can see this modulation. So we see the low frequency, and which is the modulation, and the high frequency. And if we compute the spectrum of that, the positive part of that, we are seeing the two contributions of the two sinusoids. So we see the two peaks of the two sinusoids. And in the phase, we see the phases of these two sinusoids. And now let's show an example of a real sound, a sound that includes many sine waves, like the sound of an oboe. Let's listen to the oboe first. Okay, so this is an oboe playing the A4 note, so which is around the fundamental around 440 hertz. And in the spectrum, we clearly see all these sinusoids, which are the harmonics of the sound. Here we're only plotting the first 4,000 hertz, so we're only seeing the first few harmonics. This sound has many more harmonics, but this is a good way to zoom into these shapes of the windows, and also we see the phase spectrum of that. But how do we detect the frequency, amplitude, and phase of each of these sine waves? A simple way to identify a sinusoid in the spectrum is by just focusing on the spectral magnitude, on its location, and on its height. So the location is the frequency, and the height is the amplitude of the sinusoid. So therefore, we consider a sinusoid as a peak in the magnitude spectrum. And of course, the issue is that the resolution of a magnitude spectrum is discrete, is finite, and the maximum resolution we will be able to get is half of the distance between two frequency samples, between two bins. So that's the maximum frequency resolution that we'll get in measuring a sinusoid. But we can do better than that. And a way to do better than that, and related to things that we have already mentioned, is the idea of zero padding and of spectral interpolation. So we'll be able to do zero padding to get a bigger FFT so that we get more samples, and we can also do interpolation directly on the resulting samples to even refine the value of the frequency and amplitude values. To detect the spectral peaks, we have to understand the effect of the window. And the most important factor is the window size. So if we have a particular window, and one important concept is the bandwidth of the main lobe in the spectral domain. So the bandwidth of the main lobe is B sub f, expressed in hertz, so that would be the main lobe bandwidth of the window in hertz, and that's defined as the product of B sub s, so the main lobe width of the window expressed in samples, multiplied by the sampling rate, and divided by the window size. And so that would be the width of the main lobe. And then if we consider a particular delta of the distance between two frequencies that we want to resolve, so we have two frequencies, f sub k plus 1 and f sub k, so the absolute value of the difference is the delta frequency that we want to resolve. So what would be the window size, capital M, so that two main lobes of the window are disjoint, so that we can see these two frequencies as separate peaks in the spectrum. So this equation here shows what has to happen. So M has to be bigger or equal than B sub s, so the number of samples of the window in the main lobe, multiplied by the sampling rate and divided by this delta. Or we can also change this delta as the absolute value of the difference of these two frequencies. But in many cases, this difference between the two frequencies corresponds to the fundamental frequency, because if it's a harmonic sound, the distance between two consecutive harmonics is equal to the fundamental frequency. So if we consider the fundamental frequency, this delta that we want to be able to discriminate, then the bandwidth in hertz of the main lobe of the window has to be smaller or equal than this fundamental frequency. So we see these lobes separate. And therefore, capital M, the window size, will have to be bigger or equal than B sub s multiplied by F sub s divided by F sub 0. Or if we express the period instead of the fundamental frequency, we express the cycle length as the period in samples, then this M has to be bigger or equal than B sub s multiplied by the period of the harmonic sound expressed in samples, which is this capital P. So let's show an example. Let's start from a given window, like the Hamming window, that B sub s is equal to 4, so the main lobe width is equal to 4, and we have a given sampling rate, and we have two particular frequencies that we want to distinguish, the ones we showed before, 400 Hertz, 440 Hertz, and 490 Hertz. So the difference is this 50 Hertz. So we can calculate capital M that allows us to distinguish these two frequencies. So capital M will have to be bigger or equal than B sub s, 4, multiplied by sampling rate, 44,100, and divided by this difference, the absolute value of this difference, which is going to be this 50 Hertz. And that M will be 3,528 samples. So if we take 528 samples of this signal and we compute the DFT of, with some zero padding so that we see a smooth spectrum, we see this magnitude spectrum. Clearly, we see two clearly distinct peaks, each one corresponding to the transform of a Hamming window. And of course, in the phase spectrum, we also see the corresponding phases. And let's see what happens with different sounds. So for example, if we have the sound of an oboe that has a particular frequency, which is 440 Hertz, what should be the M? So if we take an M of 401 samples, these 401 samples basically corresponds to 4 periods of this oboe sound. Okay? And then so if we compute the DFT of this signal multiplied by a Hamming window, and again with a zero padding to get an N equal to 1024, we see these harmonics quite clearly separated. So each harmonic corresponds to one main lobe of this Hamming window, and they are quite clearly one after the other. But now let's see if we increase this window size. So instead of having these 401 samples, we have twice as many. So we have 801 samples, and then we do the same thing. We apply the Hamming window, and then we take an FFT which is larger. We see this spectrum. And so here, because we took more samples, the distance that now we can discriminate is larger. So in fact, we see that the main lobes are narrower than what we even need. That is, we even see the side lobes in between the two main lobes because we took a bigger window size, and therefore we are able to discriminate even more than the fundamentals frequency. On the topics covered until now, there were quite a bit of references, but starting from this lecture on, the techniques are more specific to music applications, and quite a bit less has been published. This is good for me for the course. You'll have to pay more attention to what I'm going to be talking about. Anyway, so apart from the standard references in Wikipedia, you can find a little bit about it, and of course, again on Julius' references, you can find quite a bit more and more in-depth discussion about these things. And that's all for this lecture. We have presented the sinusoidal model, a sound representation that can be built on top of the short-time Fourier transform. and that can reduce the amount of spectral information to be considered. However, to use it, we have to understand a bit about spectra and about windows. Hopefully, you understood some of that in this lecture. Now we have to complete the explanation of how to identify the spectral peaks and how to synthesize them. So this will be covered in the next two theory lectures. So thanks for your attention.